And this matrix would contain the reduced samples. So because the reduced sample is two-dimensional, you could imagine the size of this matrix would become what? Originally it's 5 by 4. Then in the reduced space, this would become what?
2 by 4.
So don't forget, each row represents one sample. You don't change the number of samples. 5 by 2. Okay? And here, this array contains the variations for each component. And how many elements does this array should have?
Variation for each element?
For each direction?
2 then.
No.
3.
4. So original space is 4. We just mentioned. If the space is P, then you would expect P principal components. Alright? And for each component, you want to have a corresponding variation number.
No, I said 2 because thing is two-dimensional.
Oh, right, yes, it's true, yes. Right. You're right, yes. Because you want to have P variations. And here, this contains the two largest variations. Okay? And then this matrix 3 will contain the principal component direction. Okay? Corresponding to the two largest variations. Okay? And what's the size of this matrix? Because we just choose 2 directions. Alright? And this will be what? 2 by 4. Because the direction should be in the original space, which is 4-dimensional. Right? Just like here. Like here. The original space is 2-dimensional, right? And this is the first major component. In order to represent this direction, it must be what? A two-dimensional vector. Okay. So now, in our case, it's 4-dimensional, which means in order to represent each principal component, it should be a 4-dimensional vector. Does that make sense? Okay. So you can see here. If you go back to the like here, right? And this is the first principal component. How can we represent this vector, this direction? It must be what? 2-dimensional.
2-dimensional, yeah.
Okay. And in our case, the original space is 4-dimensional. That's why in order to represent each component, it must be what? 4-dimensional vector. Right? And even though the space is 2-dimensional, new space, it just represents the coordinates, all right, corresponding to the 2 new principal components. Okay, just like here, these are the new coordinates. It's 1-dimensional. But in order to represent this direction, it must be 2-dimensional. Let me reduce the size. All right, and then take a look at this. It's wrong. All right, so let's take a look at the second matrix, which represents the reduced feature space, 2-dimensional. Okay, you can see here, this is the first sample, two-dimensional. Second sample, sample number 3, sample number 4, and the sample number 5 is becoming two-dimensional. And this array represents the variation. At index 0, you can see it's 38. You would expect at index 1, the number should be smaller. Let's see what's the corresponding number here. Okay, now you can see here, at index 1, which is the second largest variation, it's 5 point something, much smaller than the largest one, which is 38 something. Okay. So you can see we just have 2 variations. And then you have the principal component direction. Okay, you can see here, because the new feature space is only 2-dimensional. All right, so we have the first direction corresponding to the largest variation. Second direction corresponding to the second largest variation. Okay, so this is how PCA works. Alright. In our case, for the future assignment, you would have a bunch of ECG or EEG signals, right? Which might be, like, say, 256 dimensional, right? And then we'd like to use PCA to reduce to, say, 20 dimensional, for example. Okay? Before we can apply the classification algorithm. Okay? All right. Now let's move on to talk about how classification works.